The next problem which we are going to look at, it consists of a wooden beam which is simply supported, and the loading is a kind of a variety of loading, as you can see. So this is simply supported between the points A and B, and it has a uniformly distributed load of 22 kilonewton per meter, and P equals to 50 kilonewton. And also this figure over here, it shows the cross section of the beam. So it is 220 mm wide and 700 mm thick, and it's a rectangular cross section, unlike the previous, the T section we are looking at. So calculating the moment of inertia, the centroid, is pretty simple. So centroid, it will be exactly at the center. It will be at a height of 350 and at a distance in between of 110 over here, right? Now let's see what the question asks. So it says that the wooden beam with the loading and the cross section is given, which is this one over here, and it asks for the maximum tensile and the maximum compressive stress due to the bending. And also it says that if Q stays unchanged, that is this UDL, it stays as it is, what is the maximum P that you can apply such that you do not exceed the allowable load, sigma allowable 13 MPa in compression or in tension over here. Now, from the looks of the problem, it seems pretty straightforward. It's very similar to what we did previously, but the only difference here is that the bending moment is not a constant uniform throughout. So technically it is not a case of uniform bending, but as we discussed, that even for the case of non-uniform bending, or bending which is not quote unquote simple bending, that if you take a very small chunk where near about where the maximum occurs, that can be approximated that at that small location that your if you take that small beam and that moment is constant at that particular place, so the bending formula or the flexure formula we derive still holds good. So compared to the previous problem, the challenging part of this particular problem is that you have to find out the shear force diagram and the bending moment diagram. I mean, you can do without the shear force diagram as well. If you're using the method of sections, you can calculate at whatever sections, at different sections, the bending moment, and you can find where the maximum is occurring. But in this problem also, you will see it's easiest to go with using the relationships between the load, shear and bending to find the shear force diagram and the bending moment diagram, and you need the shear force diagram because you remember you derive the bending moment diagram from the shear force using the relationship dm dx equals to v md minus mc equals to the area of the shear force diagram, and so on. So I'm not going to go into the details of deriving the shear force diagram and the bending moment diagram. By this point it's assumed that you know very well how to draw the shear force and the bending moment diagrams. I'm going to give for this one the reactions that we get. So if you solve this problem, first of all, from the loading itself, the reaction that you will get at this particular point over here, so this is your RA you get as 1. I have this solved already, so I'm just writing the final numbers. 105.04 kilonewton, and at this point B you get the reaction RB as equal to 90, sorry, you get 92.36 kilonewton. And so these are the reactions. So once you have the reactions, you can go ahead and solve the or draw the shear force diagram and the bending moment diagram. So while we are still at this page, I will let you get to your notebook and your pen and drawing the beam and finding the shear force diagram and bending moment diagram. After you have done it, I'm just going to go to the next page where the shear force diagram and the bending moment diagram are drawn already. So please go ahead and attempt this problem and come back after the short pause to look at the shear force diagram and the bending moment diagram. So if you have solved it correctly, this is what you should get as your shear force diagram, and from there your bending moment diagram. So see, these are the same reactions as we got in the last page. So let us go there. 105.04, 92.357. So these are the reactions. 105.04, 92.37, something like that. So let's just go ahead with the problem that we have over here. So if we go to the next page, So this is the shear force diagram and this is the bending moment diagram. So we are primarily interested in this one because we are dealing with the problem of bending that we have over here. So let's go ahead and revisit the question. So it asks the maximum tensile and the maximum compressive stress due to bending. So we know that from our fundamental relationship that is there, that my sigma x, and let me again write with the modulus sign over here, is fundamentally my by I, right? Now since the bending moment is entirely positive over here, where am I going to get the which part of the beam will be in tension? The bottom part. Remember, the positive bending moment means the beam is bending like this, sagging. So the bottom part, bottom fibers will be in tension and the top fibers will be in compression. So let's maybe go ahead and mark that over here. So the bottom fiber will be in tension. And in this particular case, it will not matter much, at least the values won't matter because it's a rectangular section. So your centroid is exactly at the center of the beam and it's same, right? So my sigma t, that is the maximum tensile stress, is going to be what? Maximum tensile stress, sigma t, is going to be the value of the moment that you have over here, that is 193.857, which is this guy, times 10 raised to 6 converting to Newton meters, times the y up to the maximum fiber. So here if you mark the centroid, so it is somewhere over here, right? So you're essentially interested in calculating this extreme distance for the compression and up to here for the tension part, and this is equal. So this is 350 mm, right? So each of these is 350. So if you have to write that over here, so it will be times 350 divided by I for this one is going to be 1 by 12 b d cube. So it is going to be 1 by 12, b is 220 times h is 700 cubed over here, right? So if you solve this one, what you will get, that sigma t comes out as 10.8 MPa. Right? So this is your maximum tensile stress that you get. Now similarly, the compressive stress acts on top over here. So here the tensile stress we calculated was the maximum tensile stress was along this fiber over here, and the maximum compressive will be over on the top fiber over here. It will be equal in magnitude because the distance is the same, the I is the same, it's just going to be opposite in sign. So you can maybe directly write, or if you want to calculate, you're welcome to. It will be minus 10.8 MPa. So that solves your part A of the problem, right? Now part B of the problem says that if Q is unchanged, the maximum load P, such that you are not exceeding that allowable stress in either tension or compression. Now tension and compression 10.8 is the same, so you just have to find the P which does not exceed that, as a result of which the bending moment does not exceed a value for which your stress does not exceed 10.8. so that automatically tells you that this moment that you are calculating, so here your P is unknown, so here you are trying to find what is your P, right? So for the P to be unknown, you are still having to deal with the maximum moment. So this moment that you have over here, this particular guy, you have to, and Q stays unchanged, Q is 22, so the moment you have to calculate now is in terms of P. So if you keep P as a variable and again draw your shear force diagram, and from there you come to your bending moment diagram, or use the method of sections, whichever suffices you will find that your M, so this is, let me mark this one as part A is completed. So now dealing with part B, so you will find that this moment M comes as a function of P, as I have done it already, so I'm going to write it over here. So M comes out as 1.57 P plus 115.56, really terrible numbers, but this is what you get, right? So M is as a function of P. Now same story, we take this guy over here, this relationship and we put it over here, and now our unknown is P, and in sigma we are going to put the sigma allowable because we do not want to exceed that, right? So here, so what you will eventually get is that 13 MPa, that is your allowable stress over here. It is going to be M times Y max, that is the distance to the top fiber, equals to M is 1.57 P plus 115.56, right, into, so this is in kilonewton meter, I should have noted this, so this is in kilonewton meter, so into 10 raised to 6 times the distance to the top fiber, so that is 350 divided by the I that you have of the section, because the section doesn't change, 1 by 12 times 220 times 700 cube, right? So if you calculate that, so the only unknown here is your this guy P. So if you calculate this, what you will get eventually is that P comes out to be 75.4 kilonewton. Right? So that solves both your part A and part B. So you see the concept of using the flexure formula to compute the stress, the tensile stress or the compressive stress, is conceptually very simple. So the catch here is that you need to be able to calculate the correct value of the maximum bending moment. So that is why I kept on telling that your adequate drawing of shear force diagram and bending moment diagram is extremely important, because you will see this chapter which we're looking at now and the next chapter also, it really heavily relies on you being able to draw correct shear force diagrams and the bending moment diagram. Imagine if you found the bending moment diagram as a mistake over here, so that naturally carries over to while you're calculating the stresses or this maximum load P that you get over here. So I hope both these two examples were clear. The most fundamental thing, remember, is always this guy over here. This is your starting point, and from there you go that to calculate the stresses, to calculate the strains and so on. Okay, all right. So with this we finished part A and part B as well. So I hope both the example problems were useful for you to understand the flexure formula and overall the theory of bending.